Good afternoon. My name is Pamela Mehanna, and today I'm going to give you a little overview on our study on major changes in the myocardial metabolome following nicotinamide riboside supplementation in a heart failure rat model. This project is in collaboration with Mathias Merixet and his team at the INSERM in France. Acute myocardial infarction, MI, is the most severe subtype of ischemic heart disease. In the last decades, mortality attributed with MI decreased thanks to better prevention and better care. As more people survive heart attacks and other acute heart conditions, heart failure is on the rise. Heart failure is the most commonly due to damage to the heart muscle caused by MI and coronary artery disease. Another adverse consequence of MI is the induction of metabolic remodeling. Nicotinamide adenine dinucleotide, so NAD, is a coenzyme central to metabolism. It is mainly involved in redox reactions and is also a substrate for enzymes that participate in the development of cardiovascular pathologies such as heart failure. In recent years, NAD stimulation has emerged as a new avenue for the development of metabolic therapies of heart failure. The main substrate for NAD synthesis is nicotinamide NAM here. Nicotinamide riboside, NR, is another precursor and holds great promise for restoring altered cardiac metabolism. In this study, we aim to investigate the impact of oral NR supplementation on metabolite levels in 4 tissues using a rat model of heart failure. So, 40 male rats were distributed into 4 groups that were either subjected to a mock surgery, so we'll call sham, or a permanent ligation of the left anterior descending coronary artery, which mimics MI. Both groups were fed either with a controlled diet, CD, or an NR supplemented diet. Untargeted metabolomics was performed on left ventricular, liver, and kidney tissues, as well as on plasma extractions for each rat. Liquid chromatography mass spectrometry, so LCMS, was used to measure metabolite levels using both hydrophilic interaction and reverse phase columns, which you can see here, more details. Sorry. Quality control steps were performed on raw data. So the steps are detailed on the poster, but in short, we removed features containing too many missing values, imputed the remaining missing values using KNN, removed constant or near constant features, seeing as these features are not likely to be informative or useful in downstream data modelization. Finally, we normalized the data using quantile normalization. We also identified 5 sample outliers using PCAs across all tissues. Unsupervised learning analysis, such as the PCAs in Figure 1, show a clear effect of the diet, so CD versus NR, regardless of surgery, most notably in LV and kidney tissues. So this is LV, this is kidney. So you can see that the CD samples cluster together regardless that if they're MI or sham, same with the NR. So we see a clear effect in LV. We also see an effect in kidney. Then we performed a linear regression models to better characterize our data. And as we see here in Figure 2, the results further highlight LV as the tissue with the strongest changes in the metabolome when we compare diets, with a larger effect in MI than in sham. So in Figure 2, I'm only showing the MI condition. In the sham condition, we observe similar results. Colors on the volcano plots represent hits that have an FDR less than 0.05. Diamonds represent annotated features. Annotations, so they are based on an in-house annotation tool from our collaborators' lab, with hits still needed to be further validated and explored. And we can see, just as an example, one of the top annotated hits in LV is the 2-methylnicotinamide, which is in the NR pathway. So a total of approximately 50% of metabolites were differentially quantified in the NR diet compared to the CD1 in the MI condition at FDR less than 0.05, and approximately 35% in the sham condition. And then we did an interaction model. So using that interaction model, we detected interaction effects between diet and surgery in plasma and LV, highlighting potential metabolite candidates that could be regulated by the NR diet. Here in Figure 3, I show 2 potential candidates in LV. For example, in the second one, the M399623, And purple is like the baseline condition, so controlled diet and mock surgeries, so CD sham. Then the value of this metabolite decreases when having an MI while still using the controlled diet, so here in blue. And when the rats were administered the NR diet, the metabolites value increased gradually, here and here, to reach almost baseline levels when having had an MI combined with the NR diet. Figure 4 shows the intersects between LV and the other three tissues. To be able to do so, we had to match metabolite features intertissues, seeing as a majority of features are not annotated. This was a bit of a challenge, but to be considered the same metabolite, we compared its mass and retention time. The mass shouldn't have a difference larger than 5 ppm, and the retention time a difference of 15 seconds or less. These Venn diagrams show that even while taking all the features into account in each comparison, so here the bold values in black, there isn't a huge overlap between tissues, so these values here, which represent the whole values here. So the red circles and numbers represent the significant features from our linear models, and we are currently investigating these intersects to further characterize tissue-specific signatures. And then finally, in an effort to better characterize the metabolites modulations between tissues, so we used metabolites shared between LV and the other three tissues and identified tissue-specific patterns of effects. So figure 5 is a heat map that uses log two-fold change values to show direction of effects between tissues. Here, the gray represents NA values. On the y-axis are the different tissues, and on the x-axis are all the metabolites shared between LV and at least one other tissue. So in this figure 5, we can observe that metabolites shared between LV and plasma, this is LV, this is plasma, are consistently modulated after NR supplementation, whereas kidney and liver signatures are less consistent with the LV patterns. In conclusion, in this study, we identified tissue-specific metabolic signatures in all 4 tissues investigated and found major changes in the cardiac metabolome following NR supplementation in rats, with a larger effect in MI than in sham. Our interaction analysis highlights putative candidate metabolites that could be regulated by the NR diet. These results provide a better understanding of how NR supplementation can alter the myocardial and extramyocardial metabolome in the context of heart failure. We still have to identify experimentally these candidate metabolites with our collaborator. Thank you very much for your attention. My contact info is at the bottom of the poster if you have any questions. Thank you very much.